Good afternoon, and welcome to the particle physics lecture. As this event is set up as a webinar, only those speaking will be visible on the screen. And if you would like to ask a question, you will have to fill the Q&A box during the talk, and then your question will be answered later on. So the Nuria lecture will be given by Hitoshi Murayama and will focus on the Higgs boson, and then we will have a panel discussion on why we need a new collider. But before the lecture, I will take about 20 minutes before Hitoshi to reflect on what we have been doing in 2022. And in 2022, the Large Hadron Collider has restarted data taking. In fact, this started in, just after the Higgs event, the anniversary of the Higgs discovery in July. And the run that we have started is called run-free. And the data that we are going to collect during this run-free will be about double the data that we have. And we will also increase the energy of the collider, going from 13 trillion electron volt to 13.6. This sounds like a small increase, about a 10% higher energy, but in fact, this is increasing the amount of Higgs boson that we are going to produce, and this will increase even larger the cross-section for heavier particle, if this particle exists. So it's really quite exciting. And the Oxford group is using the data that we have collected already before and the data that we are collecting now to zooming in into the Higgs boson even and looking at this particle even more precisely. For example, we have recently measured the Higgs boson mass with a precision of 1 per mil. This is a quantity that is not predicted by the standard model. And so knowledge of this quantity improve how we can model every other processes for the Higgs. And again, we are also developing foundational tests of the quantum theory using, for example, Higgs decays into WW and looking at the entanglement between the W's that are produced in Higgs decays. Of course, there is not only ATLAS at the LHC, but we have also the LHCb experiment. The LHCb experiment focuses on the studies of the differences between matter and antimatter in the quark sector. Since LHC started up, physicists have discovered the existence of 68 new hadrons, particles that contain quarks at LHC. And 60 of these 68 were actually discovered at the LHCb experiment. So LHCb underwent enormous upgrade. In fact, is almost a brand new experiment now. And it will collect data because of this upgrade at an astonishing rate. And this will give us exciting opportunity to probe the standard model and reach a new level of precision. So we have done a lot of work here in Oxford and in other places to rebuild and making LHC better. One of the upgrades is called the Velo detector, and this is a silicon detector, and here you can see the silicon sensor. And this detector starts at about 3 centimeters from the beam line, and then as the data is collected, it goes down to 3 millimeters from the beam, which is really amazing. And we are doing a lot of tests for this very detector. We have also played a big role in building and refurbishing the ring imaging Cherenkov detector in short reach. And when you have a particles, it will emit Cherenkov radiation. And by measuring these rings, you can distinguish the various particles produced in your event. And everything, it works. So you can see here fantastic peaks of the D0 particles that contain an up quark and a charm quark, and the jet psi particles that contain a CC bar pair. And so everything looks really good. The experiment is working. And we have a new faculty member, Snea Malde, who has joined the experiment in September 2022, and she's replacing Neville Arnew, who's retired in 2022. So for dark matter, there are, dark matter accounts for about 85% of the matter of the universe, but its nature is unknown. And there are 3 ways to tackle it. You can make it, shake it, or break it. So at a collider, we really hope that we will eventually make dark matter, and we are looking for dark matter in Atlas. But we are also looking for dark matter as a dark matter particle goes through a detector and it shakes it, for example, an atom, a nucleus of a xenon, and then this is emitting light that it can detect it in phototubes, okay? And of course, also there is indirect detection where dark matter can annihilate and give rise to standard model particles. So, the searches for dark matter in 2022 was really an important date because we completed the LZ detector, and LZ had its first physics run, and it was amazing. I mean, if you look here, this is the cross section for the weak nuclear interaction, and versus the mass of the weakly interacting standard model of the weak interacting particle. And you can see here that LZ in its run did even better than it was expected. They didn't find dark matter, but they really did even better than they expected in terms of exclusion, which is perhaps not the best, but is that what we've not found it. So also Atlas is looking for invisible decays, and we are doing very systematically. We are seeking evidence for dark matter, and we are looking for evidence of dark matter. And one of the ways to do that is to look for dark matter and search for weakly interactive massive particles that interact maybe with the Higgs boson, okay? And so what we are looking for is to search for decays where the Higgs does go into nothing. It's an invisible particle. And we have now a set limit at the level of less than 10%. And these limits are giving rise, to this plot. And you can see here that, in fact, the collider experiment is a bit of a difficult plot, but a busy plot. But here are the constraints due to direct detection. You can see them here. And here's the constraint from the collider according to different model. And you can see that they are doing even better than direct detection in the range around, for example, below 10 GeV. So they are very complementary, these two methods. Again, though, we are having a wider net now to look for dark matter. And for example, if dark matter has a mass of around 10 to the minus 12 electron volt, then the dark matter will behave more like a wave and less like a field, more more than a particle. And then for this kind of region, we are setting up experiment like ion, which will use the quantum effect in order to detect dark matter. So in the ion experiment, you will throw up a cloud of ultra cold strontium atom, a couple of them. You will throw them out, and then they will reach a maximum, they will stop and then fall down due to gravity, and they will be excited by a unique laser system. And by looking at the change of interference between these two systems, you might be able to detect or dark matter or gravitational waves. And this will set the ion experiment in its 100-meter eventual construction, will set very important limits on dark matter, very light dark matter. Again, what is also very interesting is that a 10-meter ion proof of principle is under construction and will be located in the stairwell of the Brickhoff. So we will have even a more interesting, the Brickhoff will become even more interesting in a few years. But we are not stopping there, okay? If dark matter is a light particle, it could also be produced in the decays of the hadrons that you are producing at the Large Hadron Collider. And if it's very light, it could really travel in the direction of the beam. And so we are proposing to build a new facility called the Forward Physics Facility, or PHASR, which will be underground, and it will be a long cavern. And this cavern is proposed about 620 meters from the Atlas detector. So the Atlas is here, and this cavern will be here. And this will enable searches for very light dark matter particles like dark photons, axion-like particles. And you can see here all of the reach of physics that could be done in PHASR. And again, there was already a prototype of PHASR, and you can see here the limit in terms of a cross-section and mass of, in this case, of axion-like particle. And you can see the limit of the prototype detector, which was called PHASR, and what this new facility called PHASR 2 could do. And it could really help us exploring a much larger region of phase space of light dark matter. And again, Oxford Physics is involved with that. Again, so we know that just after the Big Bang, we had the same amount of matter and antimatter. And we know that this, when the universe expanded, we had a lot of annihilation, and this created a lot of photons. And we know that in the universe that we have now, we have about 10 to the 9 photons, and more than baryonic matter, and more matter particle, and practically no antimatter particles. So, and we know also that CP violation in the quark sector is not able to explain why we don't have any antimatter in the universe today. And therefore, one place where we are looking for to understand the difference between matter and antimatter is actually the neutrino sector. And we had already some hint from the T2K experiment in Japan that maybe, there is a difference between matter and antimatter in the neutrino sector. Again, now we are playing a major role also in the construction of 2 huge detectors, one at Fermilab called Dune, and one at Hyper-K in Japan. And again, the 2 detectors, really the large detector is going to be actually in South Dakota, but the beam of neutrino is going to be at Fermilab. And the other experiment will be Hyper-K in Japan. And again, if you look here, the Hyper-K, the prediction for one of these experiments, they are expressed, the neutrino matter-antimatter asymmetry is expressed in terms of this angle theta, and the matter-antimatter asymmetry will be biggest for theta of pi over 2. And you can see that in this, if it's a asymmetry is indeed very, if the delta is really around 90 degrees or minus 90 degrees, you will have a reach of about 8 sigma to measure these angles. So very, very precise. But again, you also have a precision, also you are covering a lot of the other phase space with a precision of around 70%, with a precision of about 3 sigma. So this is very interesting. But then, once we have answered the question of matter-antimatter in the neutrino sector, it will be very important also to answer the question of what is the true nature of neutrinos? Are they Dirac particle like the electron, or they are Majorana particle? They are their own antiparticle. And again, Oxford is playing a major role and contribution to the techniques of loading tellurium in the SNO plus detector. You see really a nice picture of SNO plus detector, which is located in Canada at SNO Lab. So we are really doing a lot of physics, but because this is a lecture in which we are celebrating what we have done in 2022, I would like now to go more to the social part, okay? And, it's a celebration of the prizes that our faculty member have, or the recognitions that our faculty member have had. And again, Professor Ian Shipsey has been elected Fellow of the Royal Society. Phil Burrows, who will be part of is here and he will be part of our panel, has been appointed to CERN SPC as a Scientific Policy Committee and elected chair of the High Luminosity LHC Collaboration Board. I have been appointed PI in QP, and QP is the International Center for Quantum Field Measurement System for Study of the Universe and Particles, and is one of the centers in Japan created by the Japanese government to make science more international. And one of our students, Aime Ross, has won the post, and she's here perhaps? I mean, no. Okay, sorry. She has won a prize at the European Network for Nobel Accelerator. And again, Nobel Accelerator are very important for the future of particle physics. So well done, Amy. We are welcoming a lot of new people in PP. Matthew Capstick, a mechanical engineer in the John Adams Institute. Dennis Borde, who is a microelectronics interconnect specialist in OPMD. Patrick Green, a new PDRA in neutrino. I can't say the name of this person. I will call her just Resni because it's very difficult. She's an LHCb postdoc, and also Daniel Barro, again in neutrino, and Eleonora Rossi. I can say this perfectly. I mean, Italian is, my presentation is impeccable in Italian, okay? And in Atlas. We are welcoming, I cannot say how much students are important to the science in particles that we do in the particle physics subdepartment. We are welcoming an amazing class of 14 amazing, fantastic, superb students. And we are so happy that they've chosen Oxford. Many of them had, we had a lot of competition for many of them. And we are celebrating 13 students who have graduated in 2022, an amazing class, and they are all over the place, doing a fantastic job, many continuing in academia, actually. And again, I would like to point out that our funding council, the STFC, does not give us enough supporting to have the student necessary to exploit the data from the LHC. For example, in Germany, they have about more than twice as many students per academic than in the UK. So this is not good, but we thank the donor that established a Xing Wu scholarship. Free students are supported by this scholarship, and the Oxford Physics Endowment for Graduate, OXPEG. Again, 2 students, Seofin, I saw Seofin here. Okay, good. Okay, and they're really supported by OXPEG. So now to the student prizes. Okay, the first prize that I would like to mention is to Simon Hock. And he has received Don H. Perkin Prize for Outstanding First-Year Performance. And Simon is here as well, okay? First of all, let me tell you also that unfortunately, in 2022, we also lost Don Perkins. And we will have an event to celebrate the amazing contribution to science made by Don Perkins later in the summer, okay? He was really a giant for particle physics. So Simon is working both on Atlas, both on the pixel detector for the high luminosity upgrade. And for that, these detectors, like the Velo upgrade for LHCb, are extremely complex. When you put down a detector underground, and it's even more complex in Atlas because the pixel detector will be at the center of the experiment, it's almost like to send it to the moon. I mean, you really have to be very careful that this detector is working well. And, it has to be very precise. You have to monitor even how much glue you put in. And this is the poster that Simon has done for the Atlas UK meetings that was happened recently, which was called Lab, Glue, and Robots, because he had really to make enormous amount of testing to make sure that the glue was at that level, at the micron level, in order to put these, modules on these rings, and as a practice for what we will do for the real detector. Well done, Simon. And also is working on the measurement of tau production with Atlas to measure this in the standard model, but also to see if there are leptoquarks, because they would interfere negatively with the amount of tau that are produced by the standard model. So Simon grew up in Australia, but he's also German. And so I call him, half of the time I call him Simon, and half of the time I call him Simon, because I cannot decide if he's German or he's Australian. Yeah. So he loves cycling and skiing, and alongside physics, he has a strong personal interest in computer security. Second prize is for Gregor Eberbein. He's not here, he's at CERN, and he got the John Adam Prize for outstanding first-year performance. You can see him here. So he really likes to build experiments. He contributed to the Atlas muon spectrometer upgrade when he was at the Max Planck Institute in Munich. And he is contributing to the Atlas silicon detector, the pixel detector. And he's currently at CERN, where he's sort of building the first scale monolithic pixel detector, stitched and so thin, 50 micron things, that you can bend it, okay, around in a cylindrical shape. So, so Gregor is one of the students that we got only because we had this extra fellowship. Otherwise, we wouldn't have had the funding to get him here in Oxford. As a free time, he enjoys classical music, mountaineering, skiing, and woodworking. The third student is Wei-Jun Lee. Is in Japan, Wei-Jun. So you see how international we are, okay? And he receives the Dennis Wilkinson Prize for outstanding first-year performance, and the best talk at the 2022 symposium that we do for our students. So he's working on developing a new technique to to identify low momentum pion without tracks for T2K, one of these neutrino experiments in Japan. And he's also working to build, to assemble, as you can see here, the superfine grain detector, while he's trying to get a cup of coffee. As you know, if you are a student and a graduate student, you really need a lot of coffee. Okay? So he has shared the prize for the best talk at the symposium with Sparshita Day. Here is a picture of Sparshita. So she's working on LZ, and she's trying to improve, the capability of the analysis to push the sensitivity limit of LZ. And she's also, looking at the next generation, what you can do to do better detector to discover dark matter. So she's doing a lot of things, and she's really passionate for dark matter. And outside work, she likes to travel, makes music. She tells me that she does trap style beats. Don't ask me what they are. She bakes and forces people to let her draw them. Okay, so be careful here. You might have a portrait of you done by Sparshita. So, but really, the star of today is Hitoshi Murayama. He's going to give us a talk on the Higgs boson particles, superhero, and tour guide to new particles. And I'll try to introduce him briefly. Is he connected already? Okay, good. So Hitoshi, did his BSc at the University of Tokyo, and he did also his PhD in Tokyo. And then he emigrated to the US to join Berkeley National Laboratory. First a postdoc, and then he became a full professor in 2000 at the University of Berkeley, in California. So he's a theoretical physicist, and he works really on a wide range of topics. particle physics beyond the standard model, quantum field theory, collider physics, dark matter, dark energy, inflation, neutrino physics. And he's also a member of two experimental collaborations, Sumire, which is in astronomy, and Kamland, looking at neutrino. He is a great mentor of students. You know, some of these students are Nima Arkani Ahmed, who has done pretty well, André de Gobea, and another very, very famous, I would say, student. And he's known for his superb science communication. He's able to explain everything to everybody. He's furthermore, he's a very, you know, here is a picture of Hitoshi, you know, as a communicator at a student at the University of California, but he's also well known because he's a very accomplished double bass player. And I think that you almost was wondering if you should keep going in music or in physics. So it's really quite amazing. He's also established, you can see the t-shirt here, the Kavli IPMU, the Institute for Physics and Mathematics of the Universe, which is another one of these world premier international research center developed by Japan to build globally feasible research institute in Japan. And I think quite unique between scientists, he has addressed the United Nations about the power to unite people, how science has the power to unite people and nations. He has received many honors and prizes. He has received the Humble Prize in 2018. He has received the Breakthrough Prize for Fundamental Physics as a member of the Kamland collaboration. He has received the Yukawa Commemoration Prize in Theoretical Physics in Japan, is a fellow of the American Physical Society, of the Science Council of Japan, of the American Academy of Arts and Sciences, and is now leading the P5 panel in the US, which will set the priority. P5 stands for Particle Physics Prioritization Panel, which will set the priority of particle physics in the US for the next decade. So we were able just to grab him for this talk just before he's embarking in the P5. So welcome, Hitoshi. I leave the floor.
So as Daniela introduced me, I'm Hitoshi Murayama, and I'm speaking from Berkeley, California, in the middle of the storm, heavy rain and flooding. And unfortunately, where I live is okay. But temporarily, just 5 minutes ago, there was an internet outage. So I got disconnected for just 1 minute or so. So that might happen again. So just that I'm warning you beforehand. Hopefully it will last during my presentation, but we'll see. Anyway, so the subject of my talk today is about the Higgs boson Daniela already mentioned. And I have to say, this is a particle that is really underappreciated because, I'd like to tell you that it is a kind of superhero. Without it, we can't stay together in one piece. Without the Higgs boson, we are going to vanish in a nanosecond. So it's really keeping us together. So it's a very important particle, namely a superhero. And we discovered this particle 10 years ago, but it is sort of like we are still looking at him at distance, and we haven't gotten close up to him and shake his hand and say thank you yet. So that's something we really would like to do to understand this superhero better. And once we get to meet him and shake his hands, and I'm pretty sure that he's going to show us around to a much bigger world of new particles, new laws of physics, new symmetries. And so that's a subject I'd like to talk about today. So the Higgs boson is a particle superhero. At the same time, we believe that he's a tour guide to new particles, new symmetries, new laws of physics. So as Daniela mentioned, I'm a professor in the University of California, Berkeley. But a bit more than 10 years ago, I also started a new institute in Japan, which also Daniela visited at some point, namely Kavli Institute for the Physics and Mathematics of the Universe. And when I was starting this up, I had to spend a lot of time in Japan. My friends in Berkeley lamented that because they're going to miss him. I have to spend a lot of time abroad. And I also even gotten this long title of the director of the Kavli Institute for the Physics and Mathematics, the universe. So they complain, oh, we can't remember such a long title. So let's just keep the very beginning and end of it and make it shorter to that. I really didn't like it. It sounded like a huge responsibility to me. And fortunately, several years ago, I managed to step down and pass the torch to my successor. So I don't have to run the university anymore. So I now can think about universe a lot more than running it. So that's what I'm doing these days. So thinking about the physics, and this is a beautiful picture that came out of the James Webb Space Telescope very recently. And when you look at the picture like this, any adult or child would start thinking about some profound questions. So this is what we physicists do, right? We ask basic and deep questions. So looking at the picture of the universe, we start to wonder, how did the whole thing begin? What is fate? Where are we going? What is it made of? What are its basic laws? And why do we exist in it? And where do we come from, actually? So these are the kind of questions we physicists would like to understand. And the talk today has a lot to do with this question, why do we exist? But it also touches on many other questions here as well. Now, when you start thinking about these profound, deep questions, of course, we always have to go back to the Big Bang, the beginning of everything. And I'm sure you have all heard of this idea that universe started with a fireball, which is small, hot, and dense. And universe started to expand like crazy since then, and universe is still getting bigger and bigger. So that's the idea of the Big Bang. And we talk about the Big Bang, not just because it's the dominant theory of a kind, but actually because we have seen it. We physicists managed to take a picture of the Big Bang. So if you send out a satellite, the most recent one is the European Space Agency launched a satellite named the Planck satellite. And this satellite looked into all possible directions of the universe. And because our universe is 13.8 billion years old, if you look 13.8 billion light years away from us, you can observe the universe the way it was 13.8 billion years ago. So this Planck satellite pointed its telescope into all directions of the universe and took a picture on every possible direction. So that makes it sort of like living inside a ball. And if you stretch out the ball like you're peeling the skin of the orange and put it on a two-dimensional surface, this is how it looked like. So this is actually the picture of the Big Bang. We can still see it. So if you look 13.8 billion years away from us, you can see, aha, the universe is hot. It's still doing Big Bang. So that's what you can see in the sky. So this is the picture of the Big Bang. But I have to tell you that this picture is extremely exaggerated. So what's painted in orange is a spot that is a little hotter than the rest. What is painted in blue is a little colder than the rest. So there is some variation of the temperature of the universe here and there, but this variation is actually tiny at the level of 1 part in 100,000. So if you think of the temperature as like an ocean, which is 100 meters deep, you're talking about a tiny ripple on top of it, which is only like 1 millimeter height. So if there was such an ocean, and if you're looking on the surface of the ocean, then it would look like a completely placid mirror. So it is actually a rather boring picture, but nonetheless, that's the picture of the Big Bang. And knowing how universe got started, because you have taken a picture of it, we can ask really precise questions, like why do we exist today, and how did we survive the Big Bang? Well, I actually cheated a little bit. I told you that we took the picture of the Big Bang, but it's not quite that we have managed to see the very beginning of the universe. The picture I have shown you on a previous slide actually comes from here, when the universe was already 300,000 years old. Of course, out of 13.8 billion years, 300,000 years is nothing. So what you have seen is really the picture of the baby universe right after it was born, but not quite the moment it was born. So what you can see with telescopes is only this far. You can't go all the way back to the beginning of the universe because it's sort of like looking at the surface of the sun. If you look at the sun, we know the sun is a hot, dense ball of gas. Light can't get through it, so you can never see what's inside the sun. The only thing you see is the surface of the sun. In the same way, if you try as far as you can so that you can observe how the universe was like at the very beginning, at some point, the universe becomes so small and dense and hot, light can't get through it anymore. The only thing you can see is the surface of the Big Bang. And that's the picture you have seen on the previous slide. But if you ask the question, where do we come from? Why do we exist? You need to understand what was going on even earlier than the moment. And that's when we have to come up with different techniques to observe the earliest moments of the universe without relying on a telescope. So we will talk about one such technique as we go on. But one thing we learned by looking at this picture of the Big Bang is that we didn't have all the elements we are made of. And you remember that there's a periodic table of elements, and we need stuff like oxygen, we breathe. We have a lot of carbon in our body. We need calcium for a bone. We need iron for a blood. So we need many of these elements for us to live. But now that we have taken a picture of the Big Bang, we know that there was practically only hydrogen and helium and nothing else in the universe. So only the first row of the periodic table existed at the time of this hot, big, dense, small universe, and everything else was made sometime later. So one question we should ask when you want to know where we come from, we need to understand where these elements came from. And one thing we have learned only actually the last 20 years or so is that these elements are actually made in stars. So I told you already that the Big Bang made only hydrogen and helium. And when the first stars were born in the universe, they were made of only hydrogen and helium. But as the star shines, the way star shines is that in the middle of them, they have to actually put the hydrogen and helium together and make bigger and bigger chemical elements like oxygen and carbon and so on and so forth. And some of the big stars actually explode at the end of their lifetime, called the supernovae. So single star explodes and can become brighter than an entire galaxy. It's an amazing event, which may happen only like once in a century in a given galaxy. So it's a very rare event. But when the stars explode, they actually spread out these elements they made at the core, like oxygen and calcium, into empty space. And then those elements become dust. And that dust would just float around in empty space for a while. But at some point, they start to actually get together by the force of gravity, and that would lead to a new star, namely the child of the original star. And that child star starts also putting these chemical elements and build bigger and bigger ones into things like calcium and iron. And at the end of their life, they explode again, spread that apart into empty space. They become again dust. And that dust comes together once again to form a grandchild star. And it's believed that our sun is sort of the third generation star. So when the sun was born, there was plenty of those heavy chemical elements in the dust. And as the sun forms mostly by hydrogen and helium, the rest of the dust starts to circle around it. And the dust starts to sort of clump with each other and eventually becomes bigger and bigger and becomes a pretty big rock. That's our planet we live on. That's the planet Earth. So when the planet was formed, there was already a plenty of carbon, nitrogen, oxygen, calcium, and iron we are all made of. These are my kids when they were younger. And so what we know is that we are all stardust. But of course, we are scientists, we need to be sure to look at the moment when these chemical elements are made. Otherwise, we wouldn't believe in it. Are we really stardust? So that's something we actually managed to do. So when you look at the sun, I mentioned already that the only thing you can see is the surface of the sun. But because this reaction to put 4 hydrogen together to form helium inside the sun is happening at the core of the sun, you can never ever see it unless you come up with a new technique. Fortunately, when 4 hydrogen atoms get together to become helium, it spits out some byproducts. One of the byproducts is actually antimatter. I come back and talk about this in a moment. It's called positron. That's an anti-electron. And another byproduct is a very shy particles called neutrinos. They are so shy, they don't interact pretty much with anything, so they can get out of the entire sun without any hindrance. So the neutrinos come out straight out of the core of the sun to us. And when this reaction happens, then actually the mass gets lost. So I put that on a scale. And if you compare the entire mass before they get together and entire mass after they got together, it turns out that everything that is born after the reaction is lighter than what you start with. And somehow mass is lost. And that actually sounds crazy. So if you think of this as a collision of 2 cars on a big accident, you see a lot of debris on the ground. But when the police comes and collect all the debris and weigh the whole thing, they should weigh as much as 2 cars before the collision. And we learned this in elementary school. That's the conservation of mass. But that's actually not true. The mass is not conserved. Mass can be lost. And that's where the famous equation by Einstein comes in, E equals mc squared. So m is mass. And if you multiply that with the speed of light c twice, that actually turns into energy. So amount of mass lost in this process turns into energy, and that's how the sun shines. And now we're talking about this byproduct called neutrinos that can come straight out of the core of the sun and shining on us all the time. And they are so shy, they don't interact with us very much. But if you build a very big target, like this water tank in Japan, which that Daniela already mentioned, this tank is 40 meters high, 40 meters wide. You see poor graduate students working on a mission inside this tank over here. And using this huge tank with the 50,000 tons of water in it, you might actually see these neutrinos once in a while. So there are a huge number of them coming from the sun. As we speak, there are about 1 trillion of them going through your body every second. And you have even much bigger tank like this one, but you can still see only like 15 a day. But if you keep the focus and exposure open for 5 years to collect this 50 neutrons a day over 5 years period, you can eventually take the picture of the sun, not with light, because no light can get into this underground experiment, but with the neutrinos. So this is the picture of the sun taken with neutrinos. It's not just a picture of the sun, this is actually the picture of the core of the sun when this process is happening as we speak. So that's how we know the sun is doing this, because we have seen it using neutrinos. And this process can happen only because of rather unfamiliar force called the weak force. But we have managed to study this weak force in great detail by the particle collider experiment called LEP, Large Electron Positron Collider, which happened in a big tunnel where the LHC experiment is happening today, which Daniela described already extensively in her introduction. And by doing this experiment, we learned a lot about the nature of the weak force. So one important outcome of this experiment is that the weak force is exactly the same kind of force as electricity and magnetism. Except for one big difference. We know electricity magnetism, a long-range force. If you hold a compass in your hand, it points to the North Pole because the magnetic force coming from the North Pole pulls the needle in your hand, so it goes over a long distance. But this weak force goes over only a tiny distance, only about a billionth of the size of an atom. It's a very short-range force. So that's a big difference, but otherwise, they are almost exactly of the same kind. But this is actually already a big mystery. How come the same kind of forces now behave so different from each other? How come the electricity magnetism stayed long-range, but the weak force became such short-range force? Why is that? In addition, this distance of the billionth of the size of atom is somehow just right. So if the weak force goes over a longer distance, then this kind of reaction happens a lot more often. The whole universe becomes too radioactive for us to live. On the other hand, if the force is even more short-ranged, then this reaction doesn't happen, sun wouldn't shine, the universe would be dark, we wouldn't be able to live in that kind of universe either. So somehow the weak force behaves just the right distance so that we can exist in our universe today. So that sounds like magical. And we really ought to understand why. So one theory that came out, why the weak force became so different from the electromagnetism, is something some of you might have done actually in the laboratory experiments with your student, is the piece of superconductor. And superconductor is a very weird phenomenon that every metal has the resistance against electricity, but when you cool them down to very low temperatures, it loses resistance, which is actually great. In the future, we can build an electric grid using superconductor so that we can transmit power without any loss. But what is known to happen in a piece of superconductor is that the magnetic force gets squeezed into these tubes, which means the magnetic force doesn't go over a long distance. Mainly, magnetism has become a short-range force. So somehow, magnetism, which is supposed to be long-range force, can become a short-range force inside a piece of superconductor. So then came out the idea that maybe the whole universe is a kind of superconductor, so that the weak force, which was supposed to be long-range, somehow managed to become short-range, just like in a piece of superconductor in a laboratory. And the superconductor is being used a lot more in the industry applications. For example, Japan is now building a maglev, which is supposed to go very fast, at a speed of 600 kilometers per hour. If the train is going that fast, you don't want to have the train running on a racetrack that will shake way too much. You become very uncomfortable. So you have to actually levitate the entire train, hence magnetic levitation, and that happens because of this superconductivity. So the idea is now the entire universe is filled with this strange particle called the Higgs boson. And Higgs boson doesn't have electric charge, so light doesn't notice it. That's why it can keep going with the speed of light and can mediate a long-range electromagnetism. But the particles like the weak boson, that's a particle that mediates the weak force, notices there's a Higgs boson stuck very densely everywhere in the universe, gets bounced around by it, and that's why it can't go very far, and that's why the weak force becomes short-ranged. In addition, the particles familiar to us like an electron that is moving inside a body also bumps onto the Higgs boson and slows down from the speed of light. It can go now slowly as an effect of the Higgs boson. So that's why the Higgs boson is kind of superhero. If they weren't for the Higgs boson, the electron in our body also starts to go with speed of light. And we need to have the just right amount of Higgs boson for us to exist, because if the Higgs boson were not there, now it's frozen in the universe, very densely packed. But if some reason Higgs boson evaporates, then electrons moving inside an atom will start go with the speed of light. So it would vanish in a moment. And never mind that I'm so old that I shook hands with Einstein in a color photograph. It's kind of amazing. But both of us would also evaporate in a nanosecond if they weren't for the Higgs boson. So the Higgs boson is really the key to our existence. It's holding us together. And that's why I call this Higgs boson a superhero. And my skill on graphics is actually now very good. I had to repaint this emblem S into H for the Higgs boson. It took me like 5 hours to do so, and it's still not a very good job. But nonetheless, I hope you see what I mean. So Higgs boson is really a superhero that keeps us together in one piece. And we have discovered him 10 years ago, but we are still seeing from a distance, so we don't still know quite a bit about him. Who actually is he? Why is he frozen in the universe today? And as a result, we don't know why do we exist yet. So that's the kind of thing we really would like to learn by getting much closer up to him, shake his hands, and know more about him, and so that we can understand why we exist. And so this is, I told you, that as far as telescope can look, this is limited to the surface of the Big Bang. But we know Higgs boson somehow managed to freeze in the empty space of the universe sometime around then, when the universe was only a trillionth of a second old. So if we actually manage to see the Higgs boson, getting close up to him, meet him, understand him better, then we are also learning about these earliest moments of the universe at the same time, and to create the conditions, how the universe was like in these earliest moments, we have to really rely on the experiments called colliders, namely that you smash particles against each other at an incredible energy to create the condition how the universe was like when it was very hot, dense, and small. And so that we can redo the Big Bang in a laboratory. And unfortunately, we can restart the universe, but we can do a little bang in a laboratory. So that's how we would like to understand how Higgs boson was born and how it actually froze into empty space of the universe. At the same time, we also would like to understand how the stars were born. So this is again a picture from the James Webb Space Telescope, which costed something like $10 billion to build, but it's giving us such a wonderful pictures of the space. And what you see in this picture is something strange. So what you see is this beautiful galaxies, each of them made up of like 100 billion stars. But in addition to them, you see this strange shaped object over here. It looks like it is really stretched out. Here's another one that looks like really, really stretched out. Here's another one that's also stretched out. Here's another one over there, here as well. And you see many of these stretched out shapes of a galaxy. And there can't possibly be such a galaxy. So what's going on here is actually a trick played by the mysterious dark matter. Daniela already mentioned this. 80% of the mass in the universe is made of this dark matter. We don't know what it is, but it's actually playing tricks on us. So what I mean by this is that if you look at this collection of galaxies over here, which is called a cluster of galaxies, about 100 galaxies are living together in a village. And this cluster of galaxies is actually made primarily of dark matter. So this is actually a ball of dark matter with galaxies sprinkled inside. And because there's so much dark matter there, the force of gravity is very strong. So if you happen to look at a galaxy which is behind this cluster of galaxies from our planet Earth using this space telescope, then the light coming from this faraway galaxy falls due to the force of gravity and gets bent on its way. So this cluster of galaxies, thanks to the collection of dark matter in it with strong gravity, acts like a magnifying glass. It bends light. And many, especially older people, know if you look at the letters of the book using a magnifying glass, on the edge of the magnifying glass, the letters may look a little bit distorted. The same way, the shape of the galaxy actually look distorted and elongated in our eyes, not because the galaxy looked that way, but the galaxy has a light that gets bent because of this magnifying glass. It just happens to look to us that way due to the trick played by this collection of dark matter. To just get a feel on how it looks like, just imagine that there are plenty of galaxies running like a river behind this cluster of galaxies. And when a single galaxy comes right behind this cluster of galaxies, it looks distorted and elongated and bent. So that's how it looks like in a computer simulation. So you see this elongated stuff, but once it actually passes on and leaves behind this cluster of galaxies, it goes back to the original shape because nothing really happened to it. They are at a totally different location in the universe. Only because this dark matter is playing trick on you, the galaxy looks stretched out and elongated. And so that's what dark matter does. And it's kind of mysterious. But it turns out that we actually need that also for us to exist. So I told you that the universe started with kind of placid stage. Everywhere looked the same, but there was a little hot spots and a little colder spots. And little hotter spots had a little bit more dark matter that pulls more dark matter in by the force of gravity, becomes denser, force becomes stronger, pulls more dark matter stuff there, and it becomes the contrast between dense spot and empty spots. And in these dense spots, there are a lot of dark matter, pulls the ordinary gas made of hydrogen and helium in, and the gas would scatter against each other, emit light, and cools, and then falls into the form stars and galaxies, and hence us. But in a computer simulation, you can study the wrong kind of universe that doesn't have dark matter in it, and starts as rather sort of boring placid state. But even after 13.8 billion years, then there would be no contrast, no stars, galaxies, and us. So thanks to dark matter and its gravitational pull, we were born. So we always tell people that dark matter is kind of a mom. So she nurtured this tiny variation of temperature into full-blown stars and galaxies and us, but we never met her. So this is another big mystery about the universe. In fact, not only there's a dark matter, there's in addition something called dark energy too. So out of the entire universe, everything looks kind of dark and we don't know what they are. Only 5% of it is something we can see in a hot gas, in atoms, and we understand what they are. But the rest of the 95% is totally mysterious to us. That's the way the universe is, made of dark matter and dark energy. To study how universe was like and where the Higgs boson come from, what dark matter may be, again, we have to go back to the state of the universe early on, and we have to build these big, gigantic collider experiments to do so. And there was a famous physicist called Enrico Fermi who first came up with this idea how we might be able to reach the energy scale in the experiments so that we may have some clues on the Higgs boson and the weak force. The experiment he designed had to be as big as the perimeter of our entire planet. And, we couldn't build such a big machine. But fortunately, thanks to the development of technology and many clever ideas, we managed to shrink this planet-sized experiment down to only 27 kilometer size. That's the Large Hadron Collider. And inside this 27 kilometer circumference underground tunnel, we take a piece of proton, tiny particle, we circle it around and around like a hammer throw and get sped up faster and faster. We also do the same thing in the opposite direction, and eventually you smash them against each other to recreate the Big Bang in the laboratory, or rather a little bang. And inside this underground tunnel, it's filled with this high-tech equipment. It goes around over 27 kilometers. It's even hard to tell that it's actually round instead of straight if you're inside a tunnel. And when you smash protons against protons, you need to also have a big detector to detect everything that flies apart from this huge collision happening at the center. And this big device is what people in Oxford are working with. And compare the size of the human beings down here on the floor and also on the edge of this detector, you can appreciate how big this device actually is, which was built by thousands of physicists coming from around the world. And they've been very actually serious about public outreach from the beginning of the construction. So this is what the video they showed when they started the construction. So you see the protons come from both sides, they smash in the middle, that's the little band, a lot of things start to come out, and they have to detect them all. And now you start to see what movie they had in mind when they made this outreach movie. And they are serious folks. They go all the way to actually show this kind of picture in the video. And using this amazing instrument, they did manage to discover the Higgs boson. So two protons coming from both sides, they smash in the middle, again produces a bunch of particles in here, but two of them are particles of light, photon, showing in green. So this is an event where the smashing protons against proton actually knocked out the Higgs boson that is already frozen in empty space by putting a lot of energy into empty space. And when Higgs boson was knocked out, then it immediately disintegrated into two pieces of light. And that's what you're seeing here. So Higgs boson was already there, and using LHC, we managed to knock out from the empty space and observe it disintegrated into two pieces. So that's what colliders actually do. So this is an incredible device. So if you think about it, proton is not a very heavy object. It's like a tricycle. And here's another tricycle. And what you're doing is to speed up the proton to an incredible energy before smashing it. So it's sort of like you pedal on tricycle like crazy, you speed it up, smash them against each other, and that energy can turn into mass. That's the opposite from what's happening in the sun, where the mass is turning into energy, but we can do it the opposite way. So energy of the tricycle now turns into mass. So even though you're smashing this lightest tricycles, something heavy can come out, like an airplane and tanker. And that's indeed what collider experiments can do to produce heavy particle like the Higgs boson. But what we are also looking for is the case where you produce dark matter of the universe, that you don't see it, but you can still tell because you observe the airplane coming on one side. To balance out this big mass on one side, there must be also another big mass on the other side, but you are not seeing anything. So that's how you can be convinced yourself that you managed to create something that's heavy and invisible to you. And in fact, Daniela mentioned this already, perhaps we can make the Higgs boson first, and Higgs boson can disintegrate into the dark matter. Then, of course, you don't see the remnant of it. And that's how you might discover dark matter. So that's what I meant, that the Higgs boson might be an ultimate tour guide. Once we get close up to him and talk to him, he can show us around a bigger world that includes the dark matter. And so he is the guide for us to meet the dark matter. And Large Hadron Collider is doing an incredible job in searching for this kind of phenomenon. The Higgs boson might actually turn into dark matter. So far hasn't found it. And eventually it might hit the limit. Because whenever actually smash protons against protons, it's kind of big mess. And if you're looking for one of them being invisible out of this big mess, you can tell right away that's a pretty big job. It's not easy to begin with. And the reason why you see this big complicated thing is because you are smashing complicated things on complicated things. The proton actually is made up of 3 quarks and that are glued together by something literally called a gluon to glue them together. So what you're doing is sort of like smashing a pie against a pie. And then a lot of debris will fly out of this. And the reason I'm showing the Flammkuchen here is because the first time I gave a talk was in Germany. Maybe I should have used the pizza instead of Flammkuchen in England. But anyway, so we are smashing this complicated object to complicated object. That's why I see such a big complicated mess whenever you smash proton on proton. If you manage to smash that just the olive seed on olive seed, you see much simpler phenomena. And that will be much easier to understand what's going on. But that's actually much more difficult. It's easy to imagine you can throw a pie, and it's easy to let them hit with each other. They are big. If you're trying to throw something small, that's really hard to begin with. If you want to let them to meet each other, that's even more difficult. So that means technologically, this kind of experiment is much more difficult to smash elementary particles like electron in its antimatter part, positron. So, but if you can manage to do so, you can probably see things which had been very difficult to see in Large Hadron Collider. So that's why we physicists want to see much more crisp image of the Higgs boson by getting close up using electron and positron instead of proton and proton. And getting crisp image is very important. For example, if you see a picture like this, you might think this is a picture of the Einstein. But if you get a much more crisp image, you can tell that this is the picture of my son dressed up as Einstein on Halloween night. So you really need to understand what's going on by getting a crisper image of the Higgs boson. So if you do an experiment using the olive seed, namely the electron and positron, instead of proton and proton, what you see may be actually a lot more boring because you don't see that much stuff. But that way, you can understand what's going on much better, and you can clearly tell something is missing in this direction. So that's how we can understand things much better. So that's another thing that's great about the Higgs boson. In addition to keeping us together in one piece, he's a superhero. He can be a tour guide to a much wider universe, including dark matter. And finally, he may be another superhero of the same kind at the same time as already being a superhero. So Higgs boson may be a doubly superhero. That has to do with the puzzle, again, Daniela already mentioned about the antimatter. So antimatter sounds like science fiction, but we know it exists. So for example, these people, this is a daughter of the Marie Curie, Irene Joliot-Curie, and her husband, Frédéric Joliot-Curie, and they together send in a powerful light photon into this photographic plate that turned into a pair of a matter, electron, and an antimatter, positron. So what you can see here is that energy can turn into mass, as we talked about already. But when it does, it always makes one matter particle and one antimatter particle. It's always 1-to-1. So energy can turn into matter, and antimatter is always 1-to-1. At the same time, when matter and antimatter meet, they can annihilate back to energy, but again, always 1-to-1. So one of the antimatter particles had been produced for the first time where I live in Berkeley, California, at Lawrence Berkeley National Laboratory, and where they created the first type of antiproton. In this picture, what you see is that antiproton comes into this photographic film, meets the ordinary proton in the middle, and they annihilate. And once they annihilate, they turn into pure energy, and that energy also turns into different kinds of matter around it in this star-shaped phenomenon. So what you're seeing here is that antiproton coming in and annihilates together with a proton into pure energy, again, 1-to-1. So you can make matter and antimatter 1-to-1, and matter and antimatter annihilate always 1-to-1. And antimatter is not science fiction anymore because you're using it in hospitals these days. When you like to diagnose cancer, you typically go through a PET scan, and PET stands for positron emission tomography, and positron, it refers to anti-electron. So you actually put antimatter in your body, antimatter annihilate with matter at a cancer cell, and that emits this powerful light, and you detect where the light is coming from so that you can locate where cancer cells are. So the antimatter is something actually practical being used in hospital. Of course, word antimatter captures the imagination of people that appears in a lot of sci-fi movies like Star Trek. And if you look at this movie, the spaceship Enterprise actually runs on antimatter engine. And the reason for it is that, if you actually Google antimatter engine, you can even see the design of the antimatter engine. It's very simple. Here's a storage unit of antimatter, namely positron. All you have to do is take positron out of a storage unit, sprinkle it together with the ordinary matter, electron, and electron and positron annihilate into pure energy. Then you use that energy to run the spaceship. And the reason why that is so good for spaceship is that per unit mass, this kind of antimatter engine is 300 million times more efficient than regular gasoline. So for tiny amount of mass, you can produce a huge amount of energy, and that's why it is an ideal thing for a spaceship. You don't need to carry a lot of weight with this antimatter engine. Of course, then you might be scared if there's too much antimatter, that might be dangerous. As a matter of fact, another movie, by Tom Hanks, Angels and Demons, actually shows up CERN laboratory at the very beginning, and it shows a story that a scientist at CERN produced a 1/4 gram of antimatter without the knowledge of the director general. And this 1/4 gram of antimatter falls into wrong hands, and that's the beginning of a very thrilling movie, as you can see in this trailer. So a lot of things happening here. This antimatter falls into wrong hands. Apparently, this is antimatter, and this is floating inside this canister. And that's very important, right? Because once the antimatter touches the wall of this canister, it annihilates and starts to produce huge amount of energy. So this antimatter needs to be levitated in vacuum. And the problem with this is that this canister operates on a battery. And once it falls into wrong hands, this bad guy places this canister in an underground cellar under the Vatican. But if you leave it there, eventually battery runs out, then antimatter doesn't levitate anymore, falls onto the floor of Vatican, which unfortunately is made of matter. And once a 1/4 gram of matter and antimatter actually explodes, then that would actually turn into a huge amount of energy, which is as big as amount of energy of an atomic bomb in Hiroshima, which is really scary. But of course, in practice, you can't produce this much antimatter, even at CERN. So somebody actually even estimated how much energy bill you have to pay to produce 1/4 gram of antimatter at CERN. It eventually costs something like $1 billion times trillion times $1 trillion. And one scientist spent this much money without the knowledge of the director general. Think about how much budget they got, right? But of course, what it means in practice is that you can never, ever produce this much antimatter in practice. So, you don't need to worry about some bad guy producing antimatter for sure. But if it does, it can be actually dangerous. The problem, though, is the universe started out with a huge energy. That's a Big Bang. And that energy turned into matter and antimatter 1-to-1. So if the universe stayed that way, then eventually universe expands and cools, matter and antimatter would eventually meet with each other, and 1-to-1, they would annihilate, and the universe would have been empty. So we were actually subject to a fate of a complete annihilation. But we are here. You are here today. So something must happen to save us from complete annihilation. Somehow, this balance was changed. Somehow, somebody picked one antimatter out of 1 billion, managed to turn one antimatter into one matter instead. And many of us think that Higgs boson might have played this role as well. Once there is a difference of 2 out of 1 billion, matter and antimatter would meet and annihilate back to pure energy, but this difference of 2 would remain, and that's us. That's how we were saved from complete annihilation. So we were saved at the expense of 1 billion friends. We should thank them. But in addition, we should thank somebody who managed to turn 1 part of 1 billion antimatter into matter somehow. So we need yet another superhero, and that could well have been the Higgs boson once again. So did he save us from a complete annihilation? And we will only know only by knowing the Higgs boson better. So to design an experiment to smash electron against positron to study the Higgs boson requires very advanced technology. One possible design is a linear accelerator instead of a circular accelerator like the one we have at CERN. And inside this linear tunnel, you need to speed up these the cherry seeds or the olive seeds, the tiny elementary particles, the electron and positron. You shine a powerful radio wave into it. And radio is a wave, and electrons ride on the wave like the surfers do and get sped up. And eventually you focus the electron and positron into a beam as small as a few nanometers, about 100 atoms large, and control them so that they can meet each other and observe rather clean phenomenon like this one, so you know what's going on. And that's the way we hope to understand nature of darkness. There's already 10% scale prototype of this kind of machine in Germany, so we know this technology already exists. In addition, there's another idea of using a bigger circular tunnel to build a machine like this, for example, in CERN or possibly in China. And by doing experiments like this, we get a close-up look of the Higgs boson so that we understand finally, why do we exist? Why did the Higgs boson freeze in the universe? Does it really talk to dark matter? And who saved us from a complete annihilation? And this is where a lot of sciences come together. I already mentioned superconductivity, which is the idea of the Higgs boson to begin with. And this is a technology being used to actually build instruments like this. Maybe high temperature superconductivity becomes useful. You're using positron, just like in medicine, and also in a tomography, like a PET scan and a CT scan, and also MRI in medicine. This is also used in a machine like this. This is actually being used to understand the structure of protein, which was very important for us to make the vaccination for the coronavirus, for instance. So it is actually used for medicine, as well as the commerce, because the CERN, after all, was a place where World Wide Web was born for scientists to actually share data across the boundaries of the nations. And that actually became the heart of the $1 trillion industry now. So all of these things actually originate from basic science, including quantum computing these days. So that's how we would like to understand the way universe works, why do we exist, and so on and so forth. And technology of building such a high energy collider experiments is also being studied to go even further into the future. And here's one such a prototype experiment being done using plasma accelerator so that the size of the Large Hadron Collider may become 100 times smaller once this kind of technology becomes usable. So what I told you today is starting with this big question like, why do we exist? And I told you the story, the Higgs boson is playing a major role in this question. He's the reason why we exist to begin with. He might tell us what the universe is made of, namely dark matter. And he might even have saved us from complete annihilation and tell us where we come from. And these big questions need to work on the collaboration of all sciences, not just particle physics, but also material science, biology, astronomy, chemistry, and even medicine. And the way this kind of science really bring people together is a subject when I was invited to speak at the headquarters of the United Nations in New York for some reason. I was very honored to sit on the same table as Kofi Annan, who unfortunately passed away several years ago. And I told the story how this kind of science would bring people from all around the nation and let them work together in a peaceful fashion. And we are living at a very precarious time of the war and famine and everything. But this kind of science really plays a role of bringing people together in a peaceful fashion. And in addition, we also get to meet a superhero. So that's the talk today. The Higgs boson is actually a superhero, has been underappreciated, but now you hope you know why the Higgs boson is a superhero. But also, would probably like to play a role of a tour guide to a much bigger world of new particles, new symmetries, and new laws of physics. And lastly, I'd like to show this amazing picture taken by a space probe called Kaguya. It was launched by Japanese Space Agency, and this probe went to the other side of the moon. Then this probe didn't see the planet Earth because it was in the backside of the moon. But as the probe starts to circle around the moon, it starts to observe this planet on the lunar surface. So this is not the sunrise, but it's actually the Earthrise. And I was stunned by this video. First of all, our planet is small. And 8 billion people are living together on this tiny rock. And we are fighting with each other all the time. And we are making the environment dirty, we're producing carbon, and we're actually not letting the planet being left in a pristine condition for later generations. We are really crazy. And so this kind of picture really tells me a lesson that we have to take care of this environment much better by working together. And if you look at the still image of this, it's even more stunning, looking over this, the arid landscape of craters on the lunar surface. And in comparison, our planet is really pretty. So science, the kind of thing we talked about, really brings the world together. And it also brings a new perspective on our everyday lives. And we appreciate the universe we live in all the more better. Thank you for your attention.